Hello everyone and welcome to this video. Today, we'll be discussing colloidal gold lateral flow immunoassay technology. You may not be familiar with this term, but it's likely that you've used a COVID-19 antigen test during the epidemic. In fact, you've experienced this technology firsthand. Now is a great opportunity to learn about it, so let's dive in. Colloidal gold lateral flow immunoassay technology is a unique immune detection method. It employs colloidal gold nanoparticles attached to specific antibodies to identify the existence of a target analyte, such as a protein, virus, or bacteria within a sample. Recognized for its simplicity, rapidity, and portability, this technology serves as a critical tool for point-of-care testing. It enables diagnostics outside traditional laboratory settings, thereby offering immediate results for efficient medical evaluations. Colloidal gold lateral flow immunoassays are widely used in various fields, including medical diagnostics, for example, pregnancy tests, infectious disease detection, and drug testing, veterinary diagnostics, environmental testing, and biodefense. Let's first understand what colloidal gold is and its characteristics. Colloidal gold is a stable colloid formed by the aggregation of gold particles of a specific size, produced by the action of reducing agents such as citrate, ascorbic acid, sodium citrate, and tannic acid on chloroauric acid. Due to electrostatic interactions, these gold particles maintain a stable colloidal state. As shown in the diagram below, colloidal gold particles consist of a basic gold core, atomic gold Au, surrounded by a double ion layer. The inner negative ion layer AuCl2- is tightly bound to the gold core surface, while the outer positive ion layer H+ is dispersed in the colloid solution, maintaining the colloidal gold in a suspended state between the sole particles. Colloidal gold particles have the following characteristics. First, colloidal properties. Colloidal gold particles generally have a size range of 1 to 100 nanometers. The nanoparticles are stably, uniformly, and monodispersely suspended in a liquid, forming a colloidal gold solution. Second, coloration. The color of colloidal gold particles varies depending on their size, but they generally appear red. Third is light absorption. Colloidal gold has a single light absorption peak in the visible light range. The wavelength of this absorption peak falls within the 510 to 550 nanometer range, and it varies with the size of the particle. Larger particles have an absorption peak at longer wavelengths, while smaller particles have an absorption peak at shorter wavelengths. Colloidal gold is used in lateral flow immunoassays because it is stable and easily detectable marker. It has unique optical properties that make it easy to see and quantify even at low concentrations. Additionally, colloidal gold particles can be easily conjugated to antibodies and other molecules, making it an ideal marker for use in immunoassays. Overall, colloidal gold is a reliable and cost-effective marker for lateral flow assays, making it a popular choice in the field. Now, let's move to the colloidal gold lateral flow immunoassay. As shown in the diagram below, a colloidal gold lateral flow immunoassay test strip typically consists of the following 5 components. One is the sample pad. The sample pad is located at the front end of the test strip and is used for sample application. It controls the flow rate of the test fluid, which would be whole blood, serum, plasma, urine, or saliva, ensuring that the fluid flows into the gold-labeled conjugate pad at a uniform rate. If some reagents are added to the sample pad and the pad is treated with a specific treatment solution, it can better facilitate the specific binding of the target molecule, such as antibody or antigen, labeled with a color marker to the target molecule in the test fluid. The conjugate pad is the carrier of the colloidal gold-labeled target molecule receptors. When the test fluid flows through the sample pad and the gold-labeled conjugate pad, the colloidal gold conjugates are released from the conjugate pad and specifically bind with the target molecules in the test fluid to form immune complexes. These complexes then flow together with the test fluid towards the nitrocellulose membrane. Third is the nitrocellulose membrane. The nitrocellulose membrane is the most important part of the test strip because the final detection result is directly displayed on this membrane. There are generally two lines on the nitrocellulose membrane: the test line or T line, used to determine the detection result, and the control line or C line, used to determine if the test is valid. Nitrocellulose membrane is used as a membrane material due to its high binding capacity and ability to immobilize biomolecules. This comes from its porous and hydrophilic nature. Nitrocellulose is composed of cellulose nitrate, which contains nitro groups that cause the cellulose fibers to become highly reactive towards nucleophiles. During the manufacturing process, nitrocellulose membranes are typically treated with a mild alkaline solution to deprotonate and activate the nitro groups on the surface. This creates a positively charged surface that allows for electrostatic interactions with negatively charged biomolecules such as proteins, nucleic acids, and antibodies. Additionally, the porous structure of nitrocellulose allows for physical entrapment of biomolecules within the fibers of the membrane, further increasing its binding capacity. It also has good mechanical strength, which enables it to withstand the rigors of the manufacturing process and the test procedure itself. Fourth is the absorbing pad. The absorbing pad, also known as the waste pad or absorbent pad, is the final component of the test strip in colloidal gold lateral flow immunoassay technology. It is located at the end of the nitrocellulose membrane and is typically made of absorbent materials such as cellulose or glass fiber. After the sample has flowed through the nitrocellulose membrane and the C line has formed, any excess gold-labeled antibody conjugates will continue to flow towards the end of the strip. At this point, the absorbing pad located at the end of the strip serves to absorb the excess liquid, preventing it from continuing to flow past the end of the test strip. This helps to eliminate background noise and improve the clarity of the test results, as well as avoid potential cross-reactivity with other test strips and to keep the area around the test clean. Fifth is the adhesive card. An adhesive card can function as a backing plate. The adhesive side of the card can be used to attach or secure different components of a lateral flow immunoassay strip, such as the nitrocellulose membrane, sample pad, conjugate pad, and absorbent pad in their correct positions. Here's the structure of a gold-labeled immunoassay test paper. The 5 elements are linked sequentially to create a strip for the immunoassay test. To initiate the test fluid is applied onto the sample pad. Through capillary action, the sample moves into the conjugate pad where it interacts with the colloidal gold receptors, resulting in the formation of an immune complex. This complex then travels further along the strip, passing over the nitrocellulose membrane and binding to the antibodies present on the membrane, generating a visible red line. Any surplus gold-labeled antibody conjugates continue to move towards the absorbent pad. The test results are determined qualitatively as follows. The test result is interpreted based on the presence or absence of the T and C lines. If only the C line appears, the result is negative. If both the T and the C lines appear, the result is positive. If the control line C line does not appear, it suggests that the test has not functioned properly or that the reagents have lost their activity, rendering the test result invalid. In such cases, the test should be repeated. In conclusion, we hope that you found this introduction to colloidal gold lateral flow immunoassay technology informative and helpful. This is the first part of our discussion, and in the next video, we will be discussing into the various applications of this technology in different fields, from medical diagnostics to environmental testing. Thank you for watching, and see you in the next episode.